Hello and welcome to this lecture. We are going to study in this lecture one of the most important type of operators in all of linear algebra, which is called the self-adjoint operator. It's extremely popular in practice. In fact, you can say without any doubt that if you're not sure what an operator should be, you can sort of assume it's self-adjoint and proceed. So it's not a it's so prevalent, it's so common that everybody uses this. It's got wonderful properties, these self-adjoint operators, and they're very useful and simple to describe as well. So we'll look at why that is so. You'll see from the properties. It'll be sort of clear to you why self-adjoint operators are very important. Okay, so let's get started looking at self-adjoint operators. Quick recap. This is a new week, so let's just do a sort of a good recap. We started by defining these abstract vector spaces over a scalar field, restricting to real or complex fields in this class, and then we saw how there is this matrix representation for linear maps from one vector space to another. Notion of basis, dimension, linear independence, all of these enter the picture. And there's this fundamental theorem of linear maps, which relates the null space and range space of a linear map, and this helps us solve linear equations Ax equals b. Okay, and these four fundamental subspaces of a matrix or a linear map are important to understand, and the various relationship, how row space and null space have intersection, which is trivial, etc. All of that is something that one needs to be careful about. So think about that carefully, the various intersections between these spaces and properties that they have. Then we looked at invariant subspaces, particularly one-dimensional invariant subspaces, which leads us to the definition of eigenvectors, eigenvalues, and then we found that there is a basis in which any operator, any linear map becomes upper triangular. Okay, so that's a good result to have. And then in particular, if you have basis of eigenvectors, then the linear map becomes diagonalizable. It's represented by a diagonal matrix, which is the simplest form of a linear operator in some sense, right? And then we looked at inner product spaces, and we saw inner product spaces bring in this notion of orthogonality, and that helps us solve non-trivial problems like distance from a subspace. And also we saw that there is an orthonormal basis with respect to which any linear map is upper triangular. So these are some nice results we saw. And just last week we looked at a joint of a linear map, and it is a map which connects the inner products in one from V to W. If you have a linear map from V to W, the inner product between TV and W and V and T star W are the same. Okay, so this is this linear map which is the adjoint, which nicely connects it. And then there was this nice relationship that the null of T and the range of T star are orthogonal complements of each other. Okay, so that picture is important. We'll dwell on this a little bit more as we study more in this lecture. Okay, so this lecture is all about self-adjoint operators. Okay, so let's start with the definition of what they are. Once again, we'll start with the finite dimensional inner product space. So this is what gives us the adjoint and all that. So we start with the finite dimensional inner product space over a real or complex field. Here's the definition. An operator T from V to V is said to be self-adjoint if T equals T star. Okay, so the definition and the word are very clear. Self-adjoint, the operator is its own adjoint. Okay, so T equals T star. In other words, right, what is the definition of the adjoint? TV comma W is V comma T star W. Now if you have a self-adjoint operator, TV comma W and V comma TW are exactly the same. Okay, so this calls for a bit of a picture and some description, so let's do that. Okay, so you have V. Okay, I'll make another copy of V to sort of drive home the point, but remember these are all the same. Both of these are the same. There is this null of T, and there is range of T. So let's say we'll put it like this. Okay, and then null T, and then sort of T maps you from V to the range, and then null gets mapped to, let us say, the 0, which I will put at the end. Okay. Now, what about T star? T star we know is going to map V to V again, but it will take you to a range which is orthogonal complement of null T, right. So, range of T star is an orthogonal complement. So, in that case it is not going to intersect much with null T. So, you would have something like this, right. So, this is probably range of T star. Okay, so that takes, that's so let me just do this properly. Maybe I should do another color for this. So T and T star are sufficiently distinguished, and you would have a null of T star, which is going to be the orthogonal complement of this is null of T star, range of T star, okay, T star, and then you have T. Okay, so this is sort of the picture we have in mind with T and T star. Now notice what happens when T is T star. Okay, a lot of things here are going to sort of coalesce, right. So, if T is T star, then range of T and null of T are the same, null of T star and null of T are the same. So, all sorts of orthogonality is going to happen and things are going to really collapse. Okay, so that is one way of viewing it, and the other way of viewing it is, if you look at a V, if you look at an arbitrary V, so maybe I should do it in a different part here. So, let me do that separately. Another way of viewing it is this inner product. Okay. So, V takes you to TV and you have a W, right, and then there is this inner product TV comma W, right, and then W takes you to T star W, and this inner product V comma T star W, and both of these are the same. Okay, so this is the picture with respect to the adjoint. Now notice what happens when you have self-adjoint. The same T is going to take you back. So, V comma T W and T V comma W are the same. Okay. So, remember this picture of what an adjoint should do and what happens when the operator is self-adjoint. So, this will sort of help you visualize, if you think that is useful, what is going on between these kind of things. So, self-adjoint means the operator becomes its own adjoint. Okay. So, it is most useful to think of it in terms of matrices. Okay. So, yeah, it's one thing to visualize the linear map itself and what's happening with the null space and range space, but if you think in terms of matrices, things become much more concrete. So, let us say we have an orthonormal basis for V with respect to which you have a matrix for T, and that's M of T. Okay. So, it is going to be a square matrix. Since we are in finite dimensions, this will be clearly a square matrix. Okay, n cross n. And what is the matrix for the adjoint? It is a conjugate transpose of this matrix, right. So, when is T self-adjoint? If the matrix is equal to its conjugate transpose. So, let me just do this A transpose and then conjugate. Okay. So, this is the property. So, you do transpose of the matrix and take conjugate, you should get the same thing. So, what does that mean? A equals A transpose. So, if you have Aij somewhere here, okay, and Aj somewhere there, Aij equals Aj conjugate, that is it. Okay, so this is the definition. So, if you're starting to fill out a matrix, okay, you want to construct a self-adjoint operator by constructing its matrix, you start filling out the entries of a matrix. For an arbitrary linear map, you can put whatever entry you want everywhere. For a self-adjoint linear map, you are allowed to freely pick only elements on top of the diagonal matrix. What will happen to the bottom of the diagonal matrix? It will transpose and become conjugate. Okay. Not only that, notice what happens to AII. So that implies AII is real, right. So on the diagonal you should put real values and start putting whatever complex values you want on top of the diagonal, and below the diagonal it will simply transpose and you can construct by this. So it's almost like with you have like half of the degrees of freedom in picking your linear map, and you can get a self-adjoint linear map. Okay. So that's a good picture to have in mind. This is a very good picture to have in mind to describe a self-adjoint operator. In a more abstract sense, you can think of what happens. I'll tell you what happens in the next slide. You'll see the null T star, range T star, all of them sort of become the same. Okay. So this self-adjoint also has other popular names. In complex spaces it's called Hermitian symmetric matrices. In real spaces it's simply called symmetric matrices. So what happens if it's in real space, all your matrix entries are real, so there's no conjugation, right? Conjugation is the same, so it becomes symmetric, as in above the diagonal is equal to below the diagonal, and diagonal is whatever you want. In complex, I described to you what has to happen. Diagonal you have to put real values, and above the diagonal you put whatever complex values. When you conjugate, you will get the transpose location. Ij and Ji are conjugates of each other. Okay, so this is the self-adjoint operator definition. Hopefully it was clear. You can see you can easily construct self-adjoint operators, and there are quite a few of them, right? So you still have like half of the entries of the matrix to fill. So you can, there's quite a few self-adjoint operators out there. Okay, so a couple of important properties. In the list of these lectures, we'll just keep looking at properties of self-adjoint operators, and you'll see eventually by the end of this week, you'll see why they are so important. Okay, so the first and easy property is null T equals range T perp. Okay, so if T is self-adjoint. So you can see why this is true, right? So null T is always range T star perp, and if it's self-adjoint T equals T star, so your T becomes like this. So now you can see what will happen if you have a self-adjoint operator, right? So you have V and you have range of T and then null of T, and these two are going to be perpendicular to each other. Okay, so these are all orthogonal complements of each other, null T and range T, and that's a good picture to keep in mind for Hermitian or self-adjoint operators. Another very interesting property is TV comma V. Okay, so we saw that there is some real thing going on. Even in the Hermitian symmetric, we saw suddenly the diagonal values have to be real even in a complex space, right? So we saw why that is true, because the conjugation has to be the same. So this is sort of like an extension of this. So what this says is if T is self-adjoint, then TV comma V. So you take V and then look at what happens when you hit it with T. So it goes to TV. And if you do TV comma V, the inner product of TV comma V, that has to be real. Okay, you cannot have anything other than real there. Okay, the proof is quite easy. You'll see that it works out quite straightforward. See, TV comma V has to be V comma TV whole complement, whole conjugate, right? So the whole thing conjugate. This is the definition of the inner product. And here, if you look at TV comma V, it's V comma T star V, and the case where it's self-adjoint, it's V comma TV. Okay, so TV comma V is equal to V comma TV and also V comma TV complement. So V comma TV equals V comma TV conjugate. Conjugate. So these two are equal. So these two have to be real as well, right? So this is real and everything is real. So it works out based on this observation. So the fact that this adjoint takes you from the first argument to the second argument, and when you flip the two things, you have conjugacy, conjugates of each other. This is just the property that tells you this. Okay, so TV comma V seems to be something interesting. So in general, this TV comma V will play an important role when you look at self-adjoint operators. So you have V and it goes to TV. Okay, and this inner product TV comma V is something that will play a very central role in sort of deciding and understanding and characterizing what self-adjoint operators are. Okay, so it's sort of, you'll see why it sort of determines a lot of things, this inner product TV comma V. Okay, so already we see that it has to be real. Okay, the same V, you cannot have something which is not real. Okay, for a self-adjoint operator. So these are all useful. So for instance, quite often you will have you will have to decide whether an operator is self-adjoint or not. These are all easy checks you can do. So if TV comma V is not real, then you know self-adjoint, it's not a self-adjoint operator. Okay. So the next interesting case is TV comma V being 0. Okay, so forget about real. What about TV comma V is 0, right? So is that possible? What happens in those cases? What happens when TV comma V is real? What about the reverse of this? Okay, supposing TV comma V is real for all V, is it true that T is self-adjoint? So these are the kind of questions we'll sort of look at. We'll also look at eigenvalues of self-adjoint operators. That's also a very big result. Okay, so let's go forward. Okay, so here is a question on eigenvalues. So we already saw this. Once you say the linear map is the linear operator is self-adjoint, a lot of things are forced to be real, right? So in the matrix representation, orthonormal basis representation, the diagonal values are real. So we see TV comma V, the inner product TV comma V is real. What about eigenvalues? It turns out for self-adjoint operators, eigenvalues have to be real. Okay, so to understand the context, let's just ask a general question: when are eigenvalues real? Okay. Now there are two cases here. We've been looking at a case where the field is real and the field is complex. If the field is real and you say V is an eigenvector of T with eigenvalue lambda, clearly V has to be real, right? So the eigenvector itself has to be real. So TV is real, V is real, so lambda has to be real. Okay. So when you're talking about real spaces and eigenvalues and eigenvectors, there eigenvalues are always real. Okay, so there's no problem there. That's not so difficult to look at. But when you look at complex vector spaces in general, eigenvalues can be complex, right? So even if your matrix has only real entries, like for instance, here's an example, A being 0, 1, minus 1, 0. The matrix has real entries, okay, but its eigenvalues are complex, its eigenvectors are complex, okay. Such things can happen. Okay, so even with real entries, if you're dealing with complex spaces, in real spaces there will be no eigenvector here, right? So we'll look at this soon enough. Why is this example special? This example does some things. So in real there is no eigenvectors, but when you go to complex there are eigenvectors, but you know eigenvalue is complex, eigenvector is also complex. So this can happen. Okay. So what about self-adjoint operators? What happens if the operator is self-adjoint? It turns out that cannot happen. Okay. If the operator is self-adjoint, then every eigenvalue is real. Okay, so if you go back and look at this example, this is not a self-adjoint operator, right? It's not symmetric, 1 and minus 1. It's sort of like opposite to symmetry, negative of symmetry. So it's not symmetric. So we saw clearly an example where it was complex. But on the other hand, if the operator is self-adjoint, then every eigenvalue has to be real. Okay. So once again, it's not very difficult to prove, and you'll see this TV comma V, V comma TV will play a crucial role. Like I kept saying, this TV comma V, when you do take inner product after being operated on by a self-adjoint operator with itself, that becomes crucial to look at. Okay, so that controls a lot of properties. For instance, here let's say T is self-adjoint and lambda is an eigenvalue with eigenvector V. You look at this TV comma V being V comma TV, right? And then you sort of expand, start from the middle and go on both sides. V comma TV is V comma lambda V, and then lambda will come out, but lambda will come out to the conjugate. On this side, TV comma V, again lambda V comma V, because lambda V is an eigenvector, right, with the eigenvalue lambda. But this time lambda ended up on the first argument, so it will just come out as lambda. Lambda mod V square has to be lambda bar mod V square, and V is non-zero, right? Any eigenvector is non-zero, okay, by definition. So you can cancel the mod V squared, you will get lambda equals lambda bar. Okay, so eigenvalues become real. So notice this, the fact that you have self-adjoint makes a lot of things real. It's diagonal entries, TV comma V, lambda, and eigenvalues. Eigenvalues become real. Okay, so all of these are nice to see. So it looks like this self-adjoint operator is a very interesting class of the general operators. Okay, so the next question to ask is what about TV comma V? Can it be orthogonal always? Okay, so it turns out it's possible in the real case. So the example I considered before, 0, 1, minus 1, 0, is this interesting case. It's sort of like a 90-degree rotation if you think about it. If you take any real x, you will have ax comma x being 0. See so if you take x equals x1, x2, ax becomes minus x2, x1, okay, and then if you do ax comma x, you simply get minus x1 x2 plus x2 x1, and that is 0. Okay. So this is what will happen if you have real. Okay, x being real is important. Notice only when everything is real I can do x1 x2 x2 x1, otherwise I'll have to do some conjugate and things will go wrong here. Okay, so there's no conjugation here, it's all real, so it just works out in this way. Okay, so it's possible that you have a linear operator in a real space, so that ax comma x is 0 for all x. Okay, tv comma v is 0 for all v in a real space. It's possible. It's sort of like a rotation by 90 degrees, right? So think of in a real space, you can do rotation by 90 degrees. It's possible. Okay, so we saw this. So what about complex inner product spaces? Okay, so if you take the same example A, and you now look at allow for complex vectors, you can see that if you set x equals 1 comma I, ax you see is I comma minus 1, and the inner product I've shown here will become I times 1 plus minus 1 times I conjugate. So this is 1 conjugate is 1, I conjugate is minus I, so you will end up getting 2I, okay, and that is non-zero, right? Okay, so the same matrix as before in a real space gives you axx is 0 for all x real, but if you allow for x complex, you end up getting something non-zero. Okay, so there exists something complex for which ax comma x is non-zero. Okay, so what's going on in complex inner product spaces? And here is the interesting result. Okay, there's lots of interesting things you can say in complex inner product spaces, particularly when you look at tv comma v. Tv comma v is sort of enough to fix all the inner products in complex inner product spaces. So let's say we have an inner product space over complexes. If tv comma v is 0 for all v, then t is 0. Okay, so in a complex inner product space, you cannot have these 90-degree rotations. Seems strange. Okay, so you cannot have these 90-degree rotations, which make the orthogonal property come true, right? So tv comma v is 0 for all v, then t is 0. Of course, the converse of this is true, right? If t is 0, then tv comma v is always 0. So tv comma v being 0 is enough to check whether a complex linear map is 0. Okay, but in the real case, it's not true, right? So tv comma v is not good enough for you. But so tv comma v represents whether or not the complex the inner product space that this linear operator is 0 or not. Okay, so that is something nice to know. So why is this true? So here is this interesting relationship. So this relationship, it's sort of, I mean, once you look at it, it's obvious, but it's not clear why it should be true. So notice why, I mean, it's sort of clear why it should be true, but you may not be able to come up with it that easily on your own if you haven't seen it before. So it turns out tu comma w, that inner product, you can write as a linear combination of 4 other inner products. And what is special about all these 4 inner products? What is special about all these 4 inner products? They are all of the form tv comma v for some v. Okay. On the left hand side, you have a more general case, tu comma w, what seemingly is a more general case, but it ends up being a linear combination of just tv comma v for different v's. Okay, the first one v is u plus w, the next one v is u minus w, u plus iw, and u minus iw. Okay, and the linear combination involves some I and all that. Okay, so if tv comma v is 0 for all v, then tu comma w is 0 for all uw. Okay, so that's interesting, isn't it? So this happens only in the complex space. This I is very crucial. If you don't have the I, you cannot make it happen in the real space, right? So we already know the counter example is true, right? So it cannot be happening. Okay, so tu comma w is 0. So just by saying tv comma v is 0 for all v, you are actually forcing tu comma w to be 0 for all uw. So okay, this is really a property of this complex number field, complex field. I'm sorry. So that's why this is very important. Okay, so now you can set w to be tu. Okay, this is true for any w. So you set w to be tu. So you get tu equals 0 for all u. Norm of tu equals 0 for all u, which means t itself is 0. Okay, so that's the idea. Okay, so quickly one can see this result and notice how interesting it is. So lots of interesting things come together to make this happen. So this when you have any operator in an inner product space, complex inner product space, there is no self-adjoint going on here, right. So this is just any linear operator in a complex inner product space. And if you look at Tv comma V, and if that is 0 for all V, then that's enough to make T 0. Okay, but in the real inner product space, this is not true. Okay, so some interesting contrast between what happens here. Okay, so now if you force the self-adjoint property and look at Tv comma V, a lot more interesting things happen. Okay, so we saw before that if T is self-adjoint, Tv comma V is real. So that was an easy thing to prove for us. It turns out the opposite is also true. The converse is also true, not opposite. The converse is also true. Okay, what is the converse? If Tv comma V is real for all V, then T is self-adjoint also. So that's an interesting result, and the proof is sort of similar to what we did before. You look at Tv comma V minus Tv comma V conjugate. Okay, so notice when you say Tv comma V conjugate, that becomes V comma Tv, isn't it? So this is just the definition of inner product. Tv comma V conjugate is V comma Tv. Okay, and now what do I know about V comma Tv? Okay, V comma Tv is the same as T star V comma V. Okay, and then you have TVV minus T star V comma V, and that is T minus T star V comma V. Okay, so this is a general result for any T, right? Nothing to do with self-adjoint or something. For any T, this is true. Okay, so Tv comma V minus Tv comma V conjugate is T minus T star V comma V. Okay, so this is a general result. Now this is enough for us to prove what we want. Okay, so if Tv comma V is real, then the left hand side is 0, which means T equals T star, right? Easy enough to see. If T equals T star, the self-adjoint case which we knew before, if T is T star, then clearly Tv comma V is real. Okay, so both ways this is true. So that's the first result in this. Okay, so you see with this T being self-adjoint and TVV being real, all of these are very, very true. So this self-adjoint operators have so many simplifying properties, and all of this will sort of come together with these kind of simple proofs. I mean, there's nothing major going on here, but this notion of adjoint and the operator, the linear inner product being the same when you conjugate, then all that is playing the key role here. Okay. So there's one more result, and this result is also interesting. So we saw that for in a complex inner product space, if Tv comma V is 0 for all V, then T is 0. Now it turns out if T is self-adjoint and Tv comma V is 0 for all V, then T has to be 0. Doesn't matter whether you are in real space or complex space. Okay. So notice once again, contrast this with the result. If you don't put in the self-adjoint condition and only say Tv comma V is 0 and the inner product space is real, you cannot say T is 0, because there is the 90-degree rotation that makes Tv comma V 0, okay, even when T is non-zero in real inner product space. In complex inner product spaces, we know that can never happen. Now if T is self-adjoint, even if you are in a real vector space, if you have TVV being 0, then T has to be 0. Okay, so that's a nice property in real vector spaces that self-adjoint gives you. Okay, proof is not very hard. Over C, the result is true, right? So there's nothing much to prove. Over R, it turns out when T is self-adjoint, you can have this kind of a linear combination picture. Okay, so this is true only when T is self-adjoint. If T is not self-adjoint, this will not be true. You can simplify and check this. Even the previous result I did not prove for you, I just gave that result to you and asked you to check. You can just use the properties and check this. So here if you additionally use T is self-adjoint, you will get this combination. Okay, so once again you see here that these two are of the form Tv comma V. Okay, and this is true even in real. Okay, and that happens because T is self-adjoint. Okay, so Tu comma W is 0, and then you set W is Tu, and you will get norm of Tu is 0, and then that implies T is 0. Okay, so that concludes this lecture. So hopefully the definition, and it is quite a simple definition in terms of matrices, in terms of operator, And you see it has a lot of very interesting sub results going, particularly with respect to what happens with T v comma v, that in a product, and what happens with range of T, null of T, and all that with a self-adjoint operator. So there's lots of nice simplifying characterizations. Later on, towards the end of this week, we will see something called spectral theorems, which really simplify description of self-adjoint operators. We'll see it in more detail at that time, but this is the starting point. Okay, thank you very much.